This is good afternoon all. This is reshaping, Director of the Energy Systems Engineering Program in Lehigh. And I welcome you to the fourth seminar in the series, the fall series. And we have a special person. He's a former student at the ESE program. And in 2021, he graduated for last 4 years. 4 years back, he graduated. And Jasper Chumba worked for a little while at Pico. Years. But now he's with Summit Atlantic, consulting company. And the title of his presentation is Managing Customer-Sided Resources at the Grid Edge. And as you all know, this is probably the most exciting area of the grid, where a lot of activities are taking place today. So a little bit about Jasper's background. Jasper is a power flow and data analytics professional with experience in utility distribution design and engineering. He has contributed to pioneering projects in DER management and DR orchestration. His expertise includes applying power flow simulation tools to evaluate the impacts of behind the meter resource. Behind the resource integration, developing and validating utility use cases, and using data-driven insights to build business cases for innovative grid edge applications. Jasper first engaged with grid edge technologies during his time at Lehigh University, where his capstone project focused on virtual power lines. Since graduating, he has worked with 3 utilities, helping them address the challenges of the modern grid while maximizing the value of customer-sided resources. Welcome back to Lehigh, and Jasper, the stage is yours.
Thank you, Professor Shankar, for that introduction, and welcome people in the room and online. My name again is Jasper Chumba. I'm a Lehigh alumni. Did my bachelor's here in electrical engineering. And I did my master's in energy systems, graduated in 2021. My talk today will be on managing customer-sided resources at the grid edge, and I've changed the subtitle there a little bit to utility management, control, and utilization of distributed energy assets. Initially, I was going to talk a little more about the control and optimization side of it, but I think it's too narrow and focused. I wanted to just give you a broad view of what's happening at the grid edge, so that if you're interested in any of those sections, you can delve deeper on your own. So I haven't done a big presentation like this in a while, so might go fast, they might go slower. Please feel free to ask questions, stop me at any specific time. And people online, if you can't hear me clearly, just please raise the concern to Susan or Professor Rudy here. So the presentation today will start with definitions and framing, and then we'll talk about enablers and tools for orchestration of the grid edge. There's a lot of things happening in the grid edge, so there's tools and things that we need to do to ensure that the grid edge is being utilized and it's not causing issues to the electrical grid. I'll talk about why utilities should care and why they should care now. I'll look into 2 use cases, some of which I think you might be familiar, or rather case studies that I think you guys might be familiar with, just to exemplify why the utilities should care. And I'll summarize with just a few takeaways here. So without any further ado, we'll dive into the definitions here. And outside of the grid edge, when you hear about the grid edge, you think about the end of the grid. And the grid includes everything from generation, transmission lines, to the distribution substations, all the way to the customer, right? Behind the transformer. Here I'm just showing, a small portion of the grid. Think about it as a distribution grid there to the customer, and the transformer usually, and the customer meter, and whatever else the customer has at their premise. So normally the grid is just the point of intersection between the utility and the end user, which is industrial, commercial, residential customers. It refers to both the physical and the technical space. It also encompasses the business environment, which governs the interactions between the customer end and the grid. So I kind of broke it down to two things here: the physical space and the technical space. The physical space is the location, as we said, it's at or near the customer. And also the physical space will also encompass hardware that's installed, right? If you have, like, for example, this graphic here, you have solar panels or solar arrays. So that's physical equipment that it needs to be installed. You'll have an inverter. You might have an energy storage device there, right? Those are physical items that need to be installed at the grid edge. There's also, other things like a car, a flexible loads can be part of the physical equipment grid edge. And then there's the technical space, the software that manages these things. You have programmable loads, for example, you can set a timer to charge or discharge your vehicle at a specific time, or run your dishwasher at a specific time. So there's software involved in that. There's firmware that's installed, like inverters, for example. There's APIs that is used to communicate between devices and the grid. There's things like terms, which we'll define in a little bit here, but that's the software that's used to manage all these resources of the grid. And then there's the business environment, right? This, solar panels are not just installed for the sake of, right? They sell power to the grid, or they offset the power that the customer is consuming. So there's ways that the customer needs to be compensated or incentivized to participate in some programs, if it's like demand response, for example. So that is the general aspect of the grid edge. It has to be at or near the end user. It can be it can be at the front or behind the meter. I skipped that on the hardware part there. So here you can see the solar panels behind the meter. So you can see the electric kilowatt meter there. So DER, so other devices can exist in front of the meter. And most of those are normally either utility owned or like an independent power producer that owns those. But they're still at the grid edge, right? We need to deal with those. Can be utility owned, as I said. The utility can install batteries near the customer locations for built-in purposes for other grid services. Can also be customer owned. Most of the behind the meter resource will be customer owned, so the customer will own their solar, their battery, their EVs, right? Most of the time when the utility install devices, they're installing it in front of the meter. Second thing we'll talk about here, which will be common across this discussion, is distributed energy resources. I think this should be a little bit familiar to you guys, but that's just stands for distributed energy resources. So DER, so DARS in short, and it generates, stores, or impacts energy user at or near the end user. They're mostly decentralized. Some of them are small, can be larger ones. Utility-owned distributed energy resources are slightly larger. Customer-owned are normally small. You have just enough solar panels to cover your roof, or just a small battery to, act as a backup energy during outages for your house. So those will be smaller resources, but they're growing in scale in terms of, a lot of customers are adopting this, and they're causing impact to the grid. Like when there were a few customers here and there who, were just interested in testing solar, in the 1990s, right? The impact was really small, but now every customer is adopting a different type of DERs. So it's becoming harder to just have those customers connect without negatively impacting the grid, and also the grid is losing the opportunity to utilize those resources. So these small resources can be aggregated into what we call virtual power plants, which I think we'll define here next. Let's try to move this up. That's it. So virtual power plants are an aggregation of DERs into a network that can be centrally controlled in groups to provide grid services, right? So we've talked about DERs. DERs are small devices that are at every customer's location or close to the customer's location, right? They vary. It can be a solar panel, it can be a battery, it can be commercial building with flexible load. It can be EV charging, it could be, a fuel cell. It could be anything that can either generate electricity, can discharge like batteries, can be a flexible load, right? You need a way to control all those because they're small and dispersed. You need a way to bring them together and operate as a service to the grid. And so aggregators or aggregation brings those resources together in a virtual environment, but offers those grid services to the grid. So if it's capacity, for example, you will know how much capacity in total you can offer, maybe, in a specific region to the grid. And you can basically act like an actual power plant that produces large amounts of energy, right? You can be in, energy markets, you can sell auxiliary services, like voltage control or frequency control. So virtual power plants are becoming a common thing because of the increased adoption of distributed energy resources and demand response, which we'll talk about. But it's really the thing right now. A lot of utilities are looking to make different virtual power plants. Sometimes they're specific device based. Sometimes you can have a VPP or just batteries. Sometimes it can be a VPP that encompasses across different devices. But depending on the program, you can have the same utility or an aggregator can aggregate across multiple devices as well. I just wanted to pause there and see if anyone has any questions before we continue the definitions here. All right, sounds good. So I mentioned about demand response as part of things that can be, added under aggregation. But what's demand response? It's a shift or reduction in electricity usage at the grid edge in response to system needs or price signals, right? So these two graphs here you see, both of them are showing some form of demand response. Basically, you have a demand curve throughout the day that the utility has to meet. They have to supply that power or that energy to the customers. And at a specific time, the electricity demand is so high and it's lower at the other time. So at the peak time, you might not have enough supply to meet the demand and you want to reduce that. There's different approaches. I highlight two of them here, peak shaving and like load, you can call it load shifting or value filling. Like there's different terms that you can use for it, but let's call it load shifting here. You're moving the load from the peak hours to a later hour. For the devices that we just talked in the previous slide, like EVs, these batteries, solar panels, you can think of which devices can be able to perform the load shifting on the left side, right? Something that can discharge and charge like an electric vehicle. You can charge it at off-peak hours and discharge it at peak hours, right? To reduce the demand of the grid. Same with batteries. You can do the same with batteries. Same with flexible load, something that you can put on a timer or set to run at a specific time. If your dishwasher, if your washing machine can do that, right? You can set that to a specific setting and allow it to charge at off-peak hours and discharge at peak hours to offset the demand. The common one for all the other resources is peak shaving. Let's say air conditioning is part of demand response, right? You can increase a little bit your temperature in the summer so that you're not pulling, your AC is not using too much power. You're shaving the load at that specific time for a few hours just to have the grid, right? So peak shaving does not necessarily require load to be moved, but it's the same concept of reducing load at peak, because that's when the grid is constrained. Either the demand is low, the demand is high, the supply is low, or the infrastructure cannot handle increasing demand. So you can push more power through the infrastructure. So you either have to upgrade the infrastructure or you have to reduce the load at that time. So demand response is really a big part now of virtual power plants and just like grid edge orchestration. I know DES is talked about a lot, but demand response is becoming one of those that you utilize DES plus flexible loads plus other things that the customer has that can have the grid and reduce the need for grid infrastructure. And So you can have these devices be scheduled, like you can do a day ahead planning where you run power flow or you run a simulation to see what the grid will look like the next day, using like weather data and all the other information you have of the grid, and you can plan, a demand response. You can automate it, you can save, the grid, or, say a substation or circuit breaker reaches certain capacity or certain power rating is being pulled from it, you can automatically execute a demand response. And other triggers, as I say, like load shifting, for example, can be done through price signals, right? If you increase the price at peak, for example, the customer is incentivized to charge the car or their batteries during off-peak hours and discharge it during peak because it makes economical sense. And just continuing on the price signal, so there's two things that the utility normally charge customers for. One is consumption and demand. So consumption is how much energy consumed, right? The kilowatt hours. And demand is how much power you draw from the grid. So that's kilowatts, right? So the total amount of electricity used over a billing period, that's what you get. And they will tell you how much the cost for energy is, right? But also they can charge for commercial and industrial customers, mostly in the US, they will charge a demand charge. So they will look at the entire billing period and see the highest rate of electricity that you pull from the grid at one instance of time, right? And that's what they will charge you for. So something like that will incentivize customers to reduce their peak power use. And because it's mostly limited to C&I customers, utilities are starting to introduce different ways of, trying to incentivize other customers, residential customers, which is majority of the customers in the grid, to, shift load or try to alleviate peak loading constraints on the grid. So time of use rates has become something that will continue to grow, especially with a lot of aging infrastructure and grid constraints. So it also incentivize customers the same way C&I customers are incentivized by the price signals. So on the graphic there, it says how do utility companies charge for consumption of electricity, and it talks about the flat rate, the time rate, and the time of use. The common ones I would say is the flat rate and the time of use. Flat rate is where you're charged for whatever you consume, no matter how much you consume. Right? If this month you use 700 kilowatt hours of electricity, then next time you use 1,500, the price for using electricity will be the same. Tied rate is where for a specific amount, for example, the first 1,000 kilowatt hours you use, you charge at a specific price. For any extra of that, pricing either increases or changes depending on the structure. The time of use rate is basically what we just described here. And shown on the bottom graphic there, for example, they will say, what they consider peak hours and off-peak hours. Normally peak hours around the evening when everyone is coming back from work, it's still relatively, cold or warm, and you're using your air conditioning or cooling, you're cooking, you're doing everything, you're coming back from work. Everyone is using electricity, at that time, and the grid is a little bit constrained. So they will charge higher fees at that time so that you're not charging your car or you're not running dishwasher at that time, trying to push those to later times and setting those to run at off-peak hours. So they will charge you a higher price for using electricity at peak hours and lesser for using them at off-peak hours. And each utility will define those, right? They will define those for you. For example, here, this, graph is showing 15 cents per kilowatt hour for off-peak hours and two different prices for peak hour, right? And this depends also on the season. They might not have peak hours in the winter if the grid is not constrained, just depending on the utility and the needs of the grid. So I see time of use becoming something that will be used more in the future. Of course, that's based on approvals and other utility and public utility commission agreements. But time of use, in my opinion, will become a good tool to incentivize customers to do load shaving and shifting. I want to pause there again and see if anyone has any questions.
So this probably wouldn't happen, but is it possible that so many people would be trying to take advantage of like time of use free incentives that the peak eventually moves to like those hours that were originally lower demand?
Yeah, that's a potential problem, and the grid, you have to figure out who to incentivize how, which, like you have to optimize on that so that all customers are not shifting to one side. So that's a challenge that I think most people in the grid are aware of, and it's a valid point, right? How do you deal with that? How do you, if all customers start charging their card, midnight, right? It's gonna be a new peak at midnight. But midnight, maybe this, the other loads are not there. People probably, they're not watching TV, they're not running their device still, right? It might be a new peak, but I don't know if it's gonna be, the highest peak, right? It might peak at a specific time. So you need to find a way to, because this is a structure to try to shift load. So it's up to the utility to structure this so that the load is spread out. You can send price signals to customers and try to advise them when they should, perform an action, right? Let's say you charge your card, at 11, and other customers, you advise them to charge their cards at 3 a.m. Because this, if they're all like on a time or setting, right, they can just set it and forget about it. And just, the next day they'll have the vehicle charged, the batteries charged, their dishes washed. So that's a good point. Any other questions?
Hi, Mr. Brown, when you were explaining the tire rate, can you come again, please?
The time?
The tire rate.
The tire rate. So the tire rate is basically, I haven't seen it as much, but it's basically, how much energy consumed. They might charge you for the first portion of energy consumed. They might charge you as, maybe a cheaper price. The more energy you consume, they might charge you slightly higher, right? So they might say, the first 1,000 kilowatt hours that you consume will be at 15 cents, per kilowatt hour. And then the next maybe 500 consumed, it will be at 20 cents. So that's just basically breaking the price into different sections so that, maybe the higher consumers are paying slightly more than, a low consumer. But I haven't seen in practice that being used in most utilities.
They do this in my country.
They do it.
They do this in my country.
Oh, they do it. Yeah. That's a good example. Yeah, but most here, like if you right now, if you're in a utilities PPL here, they will have a flat rate for just the kilowatt hours you consume. Consume a lot of energy, you'll still pay the same price per kilowatt hour. Any other questions? All right. So we'll move beyond definitions here and talk a little bit about the integration. And here is actually an example model from my presentation 4 years ago for virtual power plant project. As my project was with DER NetSource, which was just trying to enter the aggregation market in California. And I was looking at the different models, which is still applicable now. Like this is how, basically the structure of how distributed energy resources are integrated to the grid. So from the bottom there, you see distributed energy resources. Those are normally integrated to the grid through aggregators, right? And I mean integration to the grid, I mean participating in demand response, net metering purposes to sell them auxiliary services. Of course, the distribution system operator will interconnect them, will do the studies and make sure that they can be interconnected and net metered. But it's through the aggregators that most of them will participate in the market, selling their energy to the grid through net metering in the retail, and then the same through aggregators to sell in the wholesale market to the transmission system operators or the independent system operators. So DES, as I said, can participate through distributed system operators, which is basically whoever is bringing electricity, like locally here is PPL, or through aggregators, right? They can connect. If you have a big solar farm, a slightly bigger solar farm, you can connect directly with the PPL, or you can, want to participate more often in the grid, you can go through an aggregator, so they have an opportunity to aggregate you with other people or other resources and give you more opportunity to participate in the grid. Aggregators are entities that, that manages, I think there's a type of that manages and coordinates multiple DERs to meet specific energy needs. So because of this, I think I mentioned earlier that most of the behind the meter resources are small resources. They can't really participate in the wholesale market. If you want to sell, you want to schedule to provide a certain specific amount of energy to the wholesale market, you need to have a minimum amount of energy to participate in that. So aggregators will talk to multiple, small DERs to consolidate their capacity, and they can participate in the market in that way. Same with even the distribution system. Let's say the grid wants to reduce, 1,500 kilowatt hours at a specific time, right? They want to do a peak shaving. Like if you have a solar panel, you just have 7.6 kilowatts to reduce, that's not enough. And they're not going to dispatch to just you. So they want that aggregated amount to be able to reduce the capacity to the desired levels. So aggregators play a bigger role. And I would say, the utility sometimes try to play aggregator, but a lot of times you'll have private entities, third-party entities doing the aggregation. And the distribution system operator will be an aggregator of aggregators. So basically they will talk to multiple aggregators within the system. A few times there, TSO and DSO, I think I define those as a transmission system operator and distribution system operator. I will not go in detail to that, but it's basically the transmission side and the distribution side who operates those. I'll talk about utility platforms and tools. We have, from aggregation, those communicate what we call DOMs, and the SCADA system is integrated to ADMS, and these are the utility will orchestrate the management of grid edge devices and distributed energy resources. So what's ADMS? ADMS is basically an advanced distribution management system, and it's advanced because now it integrates, distributed energy resources. It also uses, like Internet of Things to try to manage outages, restore the grid. It uses GIS to ensure the grid is being managed more adequately. So it's a software platform used by utilities to manage and optimize their power distribution. DAMS is, I think we've kind of talked about aggregation and DAMS. DAMS is basically a software platform that allows grid operators or utilities to aggregate or to manage or control a diverse portfolio of DERs, right? So while the aggregators are creating these resources, DAMS is where, if you want to plan, these resources exist, but you want to plan around them. What do you do with them? Like, what's their status at specific times? That's the tool that usually uses DAMS. And DAMS is normally under ADMS in some utilities. You can have it as a separate platform, but normally to integrate with ADMS. SCADA is supervisory control and data acquisition system. So it uses sensors, remote terminal units, and programmable logic controllers to monitor and control the power system in real time. So it can, can turn on and turn off, devices. It can open and close, but it's also a way of, collecting data, right, through those sensors and RCUs. An aggregator, as mentioned, is an entity basically that takes all the resources behind meter or in front of the meter, distributed energy resources, and makes those available for better use by the grid. Yeah. So management and control. So this is where most of my conversation was initially headed to. I wanted to go a little bit deeper on this, but I decided, as I said, to go a little bit high level, so that if you're interested in these areas, you can look into it on your own. But generally, for this conversation, I just wanted to highlight how the grid will orchestrates and utilizes their tools to manage grid devices. So on the right-hand side here, you see more grid edge dumps, right? I broke this down to utility and grid edge dumps. And on the grid edge dams, this is where, there's flexibility, services and consumer engagement. So this can be controlled by an aggregator, right? An aggregator also has their own distributed resource management systems. Where, you're signing, because you're an aggregator, you're trying to incentivize customers to sign up to be part of your aggregation. So you have to provide them access to tools. You have to be able to communicate with their devices, and then, take command or dispatch schedules from the grid and send it to the distributed energy resources. So they do program design, they do customer acquisition, so they do enrollment, infrastructure, notification and dispatch, measurement and verification. The utility can do this as well. It's just like, if they are acting as aggregators or aggregators, they will sometimes let aggregators do this part of the work for them. So program design, if you talk to an aggregator, they will have specific, programs that they're virtual power plants, so the devices are under them will participate in, right? So they will have that design. Customer acquisition is, they have to get customers to sign up to be part of the aggregation. Enrollment infrastructure, if they need to install smart devices to control, for example, your AC, or the other communication devices, right? They need to be able to install those, and the utility can do this as much as well. So just think about, a third party can do it, a utility can do it, right? They can go install, a utility can go install the communication device. They can acquire their own customers for specific programs. They can send their notification and dispatch, right? When there's a demand or there's a need, the aggregator or the utility can send notifications to dispatch resources. Measurement and verification is basically just verifying that the desired outputs or the reductions that were being aimed at are being achieved, right? You're trying to reduce something by a specific amount, you have to be able to validate it. So sometimes, you run validations, or you'll do, a post-event analysis to figure out whether you achieved your goals or not. On the grid side, it's mostly the dams is the dams is mostly for grid awareness. So you want to know where the devices are installed, what's their behavior. If you're installing a solar panel, for example, is it, is it acting accordingly? Is it following the smart inverter settings? It will scale the management, right? So you want to, for example, you have an issue with the grid, and you want a specific distributed energy resource to be turned off, or to be cut off from the grid at a specific time for some reason, right? You have to have that awareness. You have to be able to control that device. Active network management. You want to know, like this, where we run simulations. You want to know what's going on. How is it impacting the grid? If you make one change, how is it going to impact the grid, right? You'll run power flow simulations to understand what's going on. But visually, as under a DMS, you'll be able to see all the distributed energy resources, and that's orchestrated through dams. Operations and planning is the big thing that we do. So you plan, and you have to run operations, right? So for example, like demand response, like these are normally like scheduled events. You'll analyze the grid for the next 1 week and see, we'll have an overload at a specific time, or you have a grid constraint at a specific time. And operations will take, your findings. You'll have a study, and you'll find your findings, and you'll see what resources you can utilize at that specific time, and then you'll pass that to like operations basically, and they will dispatch that at a specific time, or you will schedule and it will be dispatched at a specific time. So dams can be seen in those two separate entities, where the grid has its own dams, and the grid edge aggregators, or if the utility is also participating in that, they'll have their own sort of dams. One for mostly program oriented, and the other one is the grid level management. Any questions? So why is this important now? There's been a reason. I put my perspective mostly on this. One is, as you learn through your classes here, things have changed with bidirectional flow and load flexibility, right? Customers customer choices have changed, customers are more environmentally conscious, for example, right? They're buying EVs, they're participating in energy efficiency programs. So there's an opportunity there for the utility to continue to utilize those resources. There's reliability reasons, right? Customers want more reliable grid with, climate change and, extreme weather events. Sometimes, customers are out of power for long times. And if they can help increase the reliability, for example, by having their batteries that can participate in demand response, act as, distribute energy resources, but also act as backup power during these outages, and that's a plus for them. But there's also a financial opportunity. Customers, who participate in demand response are incentivized, they're paid. The customers who participate in net metering, where they're selling their power in the retail market as well as the wholesale market, and they get, a financial compensation for that. So there's technical maturity for orchestration of the grid. So aggregators, there's a lot of players in the industry now. There's aggregators, there's enabling standards and tariffs. There's basically a lot of support for, maximizing the grid age devices, and that's driving the utilities to pay attention to what's happening at the grid age. Yes, as I said, growing market as well. So
there's no. And anybody look at what they're doing now. They're pulling together outside counsel, which is going to cost more money than we're going to. So down. And to me, the bigger issue there should have been killing the two birds with one stone on.
Hey, you're speaking. You're not on mute. Sorry for that. Sure. Yeah. So I'll talk about growing markets. So there's already a market for DERs, and there's an opportunity for the grid to continue utilizing the available resources, but this market is growing, right? The graphic on the right there shows you, how much residential DR capacity is there right now, not right now, but in 2023, right? Versus the peak demand, right? That's what the grid demands at peak, right? On the right side, it shows you how much of this same, distributed energy resource will be there versus that peak demand in 2035. You can see that's a lot. Like, if you have more distributed energy resources than the demand, that means that at one specific instance, you can meet the entire peak demand just with distributed energy resources without any of the bulk generation. So that's a really big opportunity, and it's something that the utilities need to continue to think about, right? It's really small right now. It still has value, but the future is, is really different. And if you're ready for it, it's bright. If you're not, it's a little bit. So the other thing is rising electricity demand, electrification, as electric vehicles, everything will be mostly electrified. Like every device you use in your house, cooking, heating, cooling, will be electric. And then there's now the big thing, data centers, is constraining the utility that's already constrained, right? You have to build new infrastructure, you have to source new energy generations, right? But with these distributed energy resources, you can try to alleviate that constraint and that, a sudden increase in demand. We have the issue with aging infrastructure. A lot of, the infrastructure is starting to age, and, there's been effort even from the government to try to incentivize the upgrades of this infrastructure. But what the grid devices and distributed energy resources demand response provides is an opportunity to do things like non-wires alternatives, which is basically utilizing these resources to avoid infrastructure or costly infrastructure upgrades. If you can reduce the big demands, because they occur only a few times a year, for example, in the summer and the winter. If you can reduce the demand at that time by using the behind the meter, front the meter distributed energy resources, you can avoid those expensive infrastructure upgrades. There's also an opportunity to learn and prepare for the future outlooks. So the utilities need to watch out for this opportunity, because, as I say, like, if you don't test out, you won't really be ready when the market is right, when there's more resources, you'll be running behind in that area. So the utilities are using a lot of pilots. I've personally been part of 2 pilots now to test some of these grid age use cases and just the technical needs, the level of at which the grid or the distributed system operator needs to be involved, the collaboration with third-party, aggregators. So there's an opportunity for them to test different things: electric vehicles, batteries, solar panels. So how do you integrate all this with the grid? How much value can you draw for it? Does it make financial sense? Is it something that's going to grow? It's not too valuable right now, but it's going to be valuable in the future. So that's where the utility needs to test, in collaboration with, of course, like national labs, research institutions like Lehigh, industry experts and vendors, right? There's, new technology, new devices coming into the market, like all that, the utility has to spend money to ready itself for, a future with, a well orchestrated page. But
I can't really see well. Is that a projection for 2035 on the right side?
yes.
Okay.
That's 2035. And that's by Deloitte. I think Professor, you'll share the presentation with them together. Any other question? So continuing on that right now, I mean, following on the same graphic there, this is showing the actual raw capacity that is expected to increase through 2028. So the USD capacity will grow about 217 gigawatts through 2028. That's an equivalent to 70% of an anticipated power generation additions during the same period. So it's basically saying, the amount of distributed energy resources that will be added here is basically equivalent to 70% anticipated power generation additions during the same period. So it's a really large percent of the future grid, right? If there's enough orchestration and utilization of these resources to offset the need for a lot of those bulk generation. Of course, we will need those for base loads, but a lot of this can start to eat into that and reduce the need for constructing new, fossil-based resources, right? So what are the drivers for adoption of devices and programs? The thing that's driving some of these adoptions include cost decline, right? In the 2010s, the cost for batteries and solar panels was really high. But over, the last couple of years, that cost has declined. As you see on the graphics on the right there, the drop, it dropped significantly until around 2016 for solar panels, and it's kind of flattened out. The batteries is still slightly, dropping, but as new technology, as new ways of manufacturing, as economies of scale kick in, the cost of these things go down, and it becomes more affordable for, customers, and the more adoption, the more, the more benefits we can reap of these devices. We've talked about market availability. There's been orders that have allowed these customers to participate in wholesale markets, which was, a big deal because, the retail market can be limited. If they can sell power to aggregators to the wholesale market, that increases the market availability for them. But they can always, net meter and sell to the retail market, which is, your distribution system operator, to provide both energy and auxiliary services. There's been technical advancements. I've talked about management systems like DOS, ADMS, so AMI meters, AMI and smart meters. Those AMI is like advanced metering infrastructure, basically the communication between the meter, back to the, the control center, back to the utility, right? That's how they send you bills. That's how, they can see you're out of power, right? Without coming to you to read your meter or to see anything, right? You lose power, they suddenly know that you have no power. Internet of Things allows, analytics and forecasting and other things that, are necessary to orchestrate some of this planned, like, events, demand response, smart devices, right? You can communicate to your thermostat and, you know, your air conditioner and control it remotely from command control center. So all these advancements have enabled PEF to continue having a, you know, of value to both the customers and the grid. Opens up revenue streams, as I said, the market availability, and you know, it allows for better orchestration. These environmental concerns, customers are becoming environmentally conscious, and they just are looking to reduce, you know, their carbon outputs, right? They have state, utility, you know, carbon targets. So the utility is pushing on that end, but customers are also wanting to participate in, you know, the climate change action, and they're forced to reduce that. So they're adopting EVs, as I say, renewable energy, solar panels mostly, to be a part of, you know, the environmental movements. We have utility incentives. These customers get compensated through monthly, yearly incentives to participate in programs like demand response. And then we have government interventions, you know, such as renewable energy tax credits, which enables increased adoption by, you know, reducing the cost of acquiring this device. So yeah, define some of that cost. Some of these programs, you know, vary based on, you know, the government of time, you know. So right now, I think the tax credits will be ending, but you know, the government can incentivize, the state government can still incentivize some of these adoptions. All right, before we jump into this, are there any questions? Anything you guys feel like, you know, might be driving adoption that I'm missing here?
I see the remote audience, you ask us questions, ask them to the remote audience.
Anyone online?
Yeah, I wanted to ask, how do you prioritize conflicting grid services? Let's say, for example, you have a battery, right, participating in the deferring, right? But then you have it registered for voltage support program and for like in the peak demand program. So let's say it's summer and this is the peak period where the battery is supposed to be charging, that's high voltage. But also there's high demand because everyone is still on their AC. So now these are conflicting. How do you prioritize which gets preference? Because the battery cannot do both.
So you're saying prioritize batteries from, can you refresh my question?
Yes, prioritizing conflicting grid services.
Okay.
How do you pick which has more preference over the other? Should the battery be supporting in the voltage support program, or should it be participating in peak demand?
So, let's say, like, if the utility has control, like, for example, voltage support will be like required up to some extent if you're using a smart inverter to connect to the grid, right? If you're net metered. And you know, these are inverter-based devices, those are required to support voltage up to, you know, I think 90% power factor is the requirements based on the tariffs on where you are, right? So there's minimum requirement to support. Beyond that, the customer is not obligated, right?
Okay.
Beyond that, the customers will sell their services. If you want more grid services from that customer, you'll pay. So you choose which one you want to pay for, and the utility will have to say, we want that for voltage support, or we want it for capacity, you know, deferral, right? So they can use it to reduce, you know, the demand, or they can use it for voltage, right?
Basically, our idea is to have some customers participate in the voltage program and some participate in the peak demand, but not one person registering for both.
Yeah, so I don't know if you can limit the customer in that sense, because unless, I don't know, I don't see a scenario where you can decide what the customer can do beyond what they're required, the minimum requirement for the rate. If they want to participate in this through an aggregator, for example, in another, you know, service production, right? As long as it's not conflicting, they're not providing at the same time. They can support voltage at one time, they can reduce, you know, demand at another time. So they can offer the energy and, you know, auxiliary services at different times. So I don't think you can control the customer. Maybe you can incentivize them more, but pay them a little bit more for quality support than you would for energy, for example. If it makes more financial sense for them to do that. Unless it's a regulation for an increased requirement for them to be supporting voltage that holds them, it's required for them to do that. But if it's not, like if it's not regulatory stuff, I don't think you can bind them to one specific service unless you're incentivizing them to push more towards what you want them to participate in than they are. Anyone online has any questions?
Yes, Jasper, I do.
Uh,
Um, this is Kirby Sleer.
uh,
So the government interventions, do you see them decreasing, obviously with the Trump administration doing stuff overall, or do you see this as a bump in the road and the industry has enough momentum that it's going to continue on at the same pace or maybe just a slightly reduced pace?
Yeah, I see it as just a small, hiccup on the road. I know they're ending like the tax credits for the time, but a lot of customers are, environmentally conscious, right? They'll adopt other technologies. Like I talked about EVs, batteries.
Mm-hmm.
And the grid is incentivizing this. The states, some states are, have their own like ways of incentivizing customers to adopt this because they have their own state goals. So although the federal government might cut back on some of their incentives and tax credits, I still see momentum, albeit like a little bit slowed down from either the states pushing it, the utilities incentivizing customers by providing more programs that the customers can participate and be compensated. And even some utilities are, as you'll see in one of the case studies here, helping customers acquire these resources. They are helping them lease them, they're sometimes buying some of these resources and owning them, but letting the customer, use them for, for example, like backup power.
Mm-hmm. Yep.
So this momentum might be a little bit slow, but the federal government not pushing for it, but the states and the utilities and just the general customer choice and environmental conscious customers are pushing rolling the ball forward.
Okay, thank you.
Mm-hmm. Any other questions? All right, we're almost there. A few more slides here. So I just put here the general, benefits and reasons why the utility should care. One and the bigger one, I think, is cost savings and capacity deferral. Like there's an opportunity for them to defer, expensive transmission lines, substation upgrades. There's also an opportunity for DERs. Actually, that's the same opportunity for the DERs to act as non-wires alternatives, right? Instead of building new infrastructure, raising the rating on their lines, you can, at those specific times when the grid is constrained, use behind the meter resources, front of the meter resources to meet that goal. These environmental goals, decarbonization and renewable integration, right? Customer participation in climate action. So as I said, the utility has its own goals. The customers have their own desire and drive to participate in climate action and produce, either produce the energy or produce clean energy, just basically participate in any way they can in pushing for carbon emission reduction. This reliability and power quality, this more on the grid side. So the grid is looking to be more reliable. So utilizing things like smart inverters for voltage support, frequency support, and right through during outages instead of just so the voltage right through, for example, the voltage right through. No, sorry, the right throughs, for example, is just a way of the distributed energy resource to stay online for a little bit longer when there's an outage instead of just succeeding at the same time as the outage, which will make it worse. So it tries to ride through and see if the grid will come back. Backup power, as I mentioned, batteries can be used for backup power for customers, and that kind of improves their, they'll have power during outages, and that improves reliability. Customer satisfaction. if customers participate in, for example, like demand response and other things, they feel empowered. So it improves that customer relation with the utility, new revenue streams for them through incentives, bill credits, and it aligns with the prosumer mindset. For regulatory drivers, mandate for DER integrations, so some states for mandates will have some exciting things that will encourage integration of DERs mostly. For the utilities, they might get some rate changes to allow for that. Customers might get incentives to continue integrating DERs. So some states are pushing for non-wires alternatives and clean energy, and that's rate design enable participation, as I mentioned. That helps the utilities participate more in some of these programs that might not be as financially feasible at first, but some of those rate designs might allow them to prepare for a future where those programs might be more lucrative. Risk of inaction, even the utilities don't take action right now, might result into interconnection delays and long queues, overloaded feeders, and reduce hosting capacity. Customer dissatisfaction if they can't connect because there's no more hosting capacity. So if the utilities participate in some of these pilots and test programs, they will be able to allow maximum DER integration and reduce the risk of delays and customer dissatisfaction. So if you don't mind, we're almost at the end of this presentation. So we'll talk about two case studies. The first case study is an infrastructure deferral, non-wires alternatives. And this is with CONED. So CONED, I think 2015, wanted to defer the construction of a new substation and adding some portion of transmission line to save costs, because in congested places like New York, Brooklyn, Queens, it's kind of hard to do some of these upgrades, and it's expensive. Generally, substation upgrades are expensive anyways, but with real estate in cities, it can be difficult to expand and meet the new growing demand. So the alternative way here was for them to try to find and incentivize customers to acquire demand response, not distributed energy resources, for example, like combined heat and power, batteries, and other things that can be used during those demand times, high demand times, to reduce the need for that upgrade. Because the idea what happens in the grid is there's a few times in the year where the grid surpasses the constraints, right? Whether it's the ratings or just the supply does not meet the demand. And it's a very few times in the year, maybe 10 times or less than 20. If you can reduce the need at that time using these distributed energy resources, you can save on very expensive upgrades that you will need. So this is exactly what was happening here. And they were given an initial budget by the state regulators of 200 billion with the goal of producing or reducing 52 megawatts using peak load reduction at the grid age management grid load management side, and they were able to reduce this by 2016. They were able to get that 52 megawatts for a very small fraction of the budget here. I think it was about 34 million that they spent. There were already resources out there that they were not utilizing, right? And then there was a few other things that the utility did, like conservation of voltage optimization, which is to optimize the voltage to reduce losses. And then a few utility side resources, batteries mostly, that were also used, but majority of the devices were on the customer side. So because of this success, the program was actually extended definitely. And it really proved feasibility of non-wires alternatives, and it's likely to drive back projects like this across other utilities. And anyone has ever heard about this project? Yeah.
What exactly did they do on the demand side?
So we talk about demand response, right? That's one big one, right? You have aggregators to aggregate all the other resources, distributed energy resources combined heat power, your house thermostat, right? If you can just for those specific times of the year, just turn off, your AC or increase your temperature during summer, right? So you're not pulling too hard and pulling more power. So the aggregators are getting all those resources, and at specific times when the grid is constrained, right, they will call on you or they will just automatically, increase the temperature to maybe 75, right? For a few hours, for 2 hours, 3 hours, max, right? And during that time, your entire demand goes down. And if you're doing that for multiple customers, right, and you're using other resources like EVs and batteries to discharge back to the grid locally, right? Because these systems are constrained, upstream of where you are as a customer. So if you're doing that locally and reducing that local demand, eventually that adds up, up to say 52 megawatts, right? That's specific time. So that reduces the entire constraint on the grid. And it's normally, as I say, the peak times are normally a few times a year. So they might call on you specifically for 4 times a year. And in time, they will save $1 billion of upgrades or defer it for a few years.
And was the budget used to pay back the customers?
Yeah, so it's used to create the programs, to incentivize the program participation. So a lot of this will be paid through aggregators, right? You participate for 2 hours, we increase your temperature, you're feeling uncomfortable, you need to be compensated for that, right? But in time, you said you're having the grid as well. So not all customers want to be uncomfortable for a few hours, so they don't participate. But those who participate get compensated for it. To say this sometimes a mindset thing, you're having the grid, but also getting paid for it. But yeah, a lot of this you have to be paid for it. So it's like, you're selling different services. It's the same with quality support. You're not selling, energy reduction, but you're selling something that the grid needs.
So we're basically saying that this hinges on the customer willing to participate. So how do we get them to participate? Because the customer might think, if I can pay for it, then why should I?
Yeah, and those customers don't participate, right? So these customers that don't need the money, but also these customers that might not need the money, but they're very conscious about, what they generally prefer. So the utility are free to try to communicate that to them. You're not just participating just for the sake of, $50, reduction in your bill, for example. Participating, you're part of the entire, having the grid, it's environment friendly because most of these resources, you're either reducing a lot, which reduces the need to go cold, fossil-based energy, right? You also, let's say, participating in something larger than just saving a few $100 on your bill. So there's different ways that they try to communicate, but of course, not all customers want to participate. They don't want to be uncomfortable. They don't want to change their behaviors. But that's just one example of a demand response problem. You can have a battery, right? Battery, you can use it as a backup power, but you can also sell energy back to the grid. And if the incentives are right, it makes financial sense. And that's what I say. If they structure it right, eventually it will make financial sense for you to participate in this program, to buy a battery and own a battery and participate in these programs because you get paid for it.
So all this behind the meter assets, they relies on forecast, right? On forecasting and their plan.
Yeah, so the utility will have, they plan, right? They plan and know, okay, the demand is growing, there's a new Walmart, there's a new university being constructed around here. They need in the next few months, the next 5 years, it's gonna be this much. So we focus from, the next day to, a couple of years down the road, right? So, go ahead.
My question is, what happens if the forecast happens to be accurate? How do you manage that?
So the forecast that we do on the grid side, right? Are you talking about the forecast of the resources available on the end, on the grid edge?
Yeah.
Okay, so we do include a margin of error, right? You can do a lot of data science around this. You can try to understand every time you call this device, how many of them do not respond, right? You can say 80%, you can put a round number. So you build a margin of error and include that analysis that every time we've called these devices, we expect 90% participation, right? So you already build that, and then you can add a few extra just for the margin of error. The last case study here that I'll talk about is capacity demand reduction through virtual power plants, and I'll refer to a project by Green Mountain Power in Vermont. So this one, it's one of the leading battery-based PPP innovator among utilities. They have two programs in which customers can enroll. One of them is bring your own battery. So you buy your own battery and participate in this program. You can also acquire battery through a subsidized lease option. These are mostly, actually, these are exclusively Tesla batteries that, they have a deal with Green Mountain Power to have customers. So the utility basically pays for some portions, actually for the entire portion of the Tesla battery. You have it for 10 years and then you'll have to return it to the utility. Through this program, they've been able to enroll more than 3,000 participants. As I say, I know I mentioned earlier that, some PPPs can be just device oriented, like this one is only batteries. Some PPPs can be mixed. So they've enrolled more than 3,000 participants across the programs, and it's been able to provide 30 megawatt in capacity reductions. And that equates to about 3 million of power supply cost savings year over year. So there's a lot of PPPs nowadays across the utilities. This is just one way of increasing participation is that lease option. Most utilities are not doing the lease option here. They're just either buying it outright for their own purpose, for reliability, for example. It's not normally this much number of batteries, right? This is you're asking the customer to adopt it, but you're listening to them. Most utilities will either buy it or just use whatever customers adopt. If a customer has a battery, you will utilize that. So this is a new strategy that I think will increase participation, and it's saving the customers, because this 3 million is saving both the utility and the customers on their bills. And I think that's the end of my presentation here. I have few key takeaways here. If anything from this conversation, I want to say is, grid age is dynamic and transformative, right? And it's going to continue to be so for the next decade. So, I know you guys are all doing this purpose for, you're looking at different career paths, but, I'll advise you to take a look at what's happening. It's not just the utility side, it's the aggregators, it's the equipment manufacturers, it's, the government, right? There's opportunities all over the place to try to, capitalize on this opportunity at the grid age. Utilities are adapting fast, and they're finding new ways to meet the needs of a more connected, flexible, and cleaner grid. So as preface this conversation with there's prosumers now, like the grid is not right one direction, it's bi-direction now. So right now the biggest things are the cost reduction, infrastructure referrals, and cutting carbon, right? Reducing your carbon emissions. Those are the main use cases that I've seen make the most financial and environmental sense. But there's other use cases that are still taking shape. There's a lot of room for innovation as technology and the market evolves. With that, I'd like to thank you all for listening.
Thank you.
There's more questions.
For everybody. Did we stop sharing? Okay, so we still have some time left. You guys have any questions in the online audience? Here in class?
There are some questions in the chat, Rudy.
Okay. What was the question?
Rudy, did you hear me? There are some questions in the chat.
Okay.
Yes. Alexander, do you mind asking a question?
Distributed can you hear me first off?
I can hear you.
Yes.
distributed generation assets that are just focused on generation, solar panels, geothermal, they present a risk to the grid because most of our grids were built for one direction power flow, and now they need to be bidirectional. And so customers expect the grid to work whether they're generating power or not. And so that's a risk, right? You put a lot of, let's say, photovoltaic, cloud comes over, storm comes in, customer still wants power, that's risk. So you still need a robust distribution and transmission system. That can be alleviated a little bit, like you said, with demand side, load reduction, or batteries. But that's not required right now. As a customer or end user, whether I'm industrial, residential, I can generally install whatever I want. Again, there's a risk to the system. Still need capacity if I need power. Do you see regulators, utility companies, or transmission system operators realizing that, hey, distributed systems have to be thought out fully and encompass a storage capacity so that the risk to the grid is lower when they're not operating?
Yeah, I think there's competing priorities right now for the grid. I think a lot of these distributed energy resources are being adopted, especially the generation ones, mostly because of the renewable energy targets that states, utilities have. But I agree with you, it poses a lot of challenges, and during the interconnection process, you have to analyze a lot of those risks and try to pass some of the cost to the customer. But inherently, you have these resources that are generating intermittently, right? You can't really rely on them. Still have to source from the bulk generators, right? So there's a cost there, and you're compensating them at the retail market. So there's a lot of challenges there. I haven't had a lot of talk yet, but I think it's going to be a problem once there's more of these resources that are generating. I know California is starting to deal with some of this, and I think because the main goal has been trying to integrate more renewable energy as we do, as we have spent this energy transition type of thing, they've kind of overlooked that impact, that negative impact. So batteries, EVs, and all the other dispatchable resources can help alleviate that process, but I haven't had a solidified conversation around that negative impact that it can cause to the grid.
Thank you.
What's that?
Any questions?
That's all.
Hello?
No, that's the only one. All right.
Additional questions for Jasper? Raise your hand or unmute yourself. Questions, Jasper? Yeah. There are no more questions. Thank you very much, Jasper. And Jasper was here in person, and so we had to move some things around. The next seminar was, I think it's October 20th, 2 weeks from now. Another alumni of ours will be here. He's with Form Energy. We'll be talking about this battery storage. And so we look forward to seeing many of you back here 2 weeks from now. Again, thank you, Jasper, for this presentation. Great value. Good job.
Sure.
Thank you all.
Thank you.
Good. Oh.